Welcome back to another video. In this video, I'm going to go over problem R, walk from Atcoder educational DP contest. Let's go over the problem statement. Given a simple directed graph G with n vertices numbered from 1 to n, and for each I and j, you are given a matrix integer I a of I j that represents whether there is a directed edge from vertex I to j. So a of I j first one denotes that there is a directed edge from I to j. This is given, and we need to find the number of different directed paths of length k in G modulo some value, and we will also count a path that traverses the same edge multiple times. Suppose you are given a graph like this, 2, 3, and this creates a cycle, and suppose k was 6, right? And let's say you start with 1, then in that case the path they are asking us to count a path that traverses the same edge multiple times differently. So same edge can be traversed multiple times. So this one, we will go from here to here, path length 2, 3, 4, 5, 6. So we traverse like this, then again through the same edge to arrive at the position u equals to 1. So this was one way, and similarly there can be two other ways for each starting position. So suppose starting position was 1, then we saw that we traverse this all the edges one by one 6 times to create a path of length 6, and for each of the starting position u equals to 2 or u equals to 3, we need to count it separately, and initially the answer for this case would have been 3 for k equals to 6. Let's go over the constraint. Constraints are n up to 50, which is fairly small, but k very large, up to 10 to 18. Path length is up to 10 to 18, and basically there are no self loops, so there won't be a edge like this in this graph. Okay, so before diving into the solution, let's try to create some observations. Suppose you were given a graph like this, say 1 goes 2 goes 3, 4, and let's say 4 goes to like this. You're given adjacency matrix according to these conditions. We create a graph from this, and let's say k equals to 1. As you can see, for k equals to 1, the number of paths of length 1 would be the number of edges in the graph, right? Because any edge will be a path of length 1. So in that case, k equals to 1, as you can see. And suppose k equals to 2, we saw that we need to fix the starting position first, right? So we need to fix what will be the starting position of our path. So if we traverse from u, then from u we're going to go over any element v, which is adjacent, which belongs to the adjacency list of u. So we are going to traverse to any element from the adjacency list of u, and then from here as well we are going to go over any element that is from the previous one, which is v here. So it will be adjacency of v, and this will create a path of length 2, right? So this will be a path of length 2, and we need to count the number of paths for any k, right? So this can be solved using recursive top-down approach. So we need to fix what is the starting position and also what is the length of path that we need to keep traversing the entire graph as. So the main idea is to start with at any position and keep on visiting. Suppose we start with length L at a starting position u, and then we arrive at any node v which belongs to the adjacency list of u, which would be the next element that we can take in the path. And here, if we arrive here, we are going to have a path reduced by 1. So this is how the entire flow will look like. There might be cycles, but we are allowed to take the same edge twice. So this approach, the straightforward approach, is going to look like this. The answer is initialized with 0, which counts the number of paths of length k, and for each starting position of nodes from 1 to n, we are going to count all the paths of length k starting from this position of length k, right? So this is length, and this is the starting position u that we saw earlier. And let's see what this function does. This takes the starting position and what is the length remaining. So we start with k, then if we move on to the next adjacent one, it becomes k minus 1, then again it will become k minus 2, and so on until it becomes 0. When it becomes 0, that means we have arrived at the ending node of the path, which was of length k, right? And this is the condition that makes sure that we count a way. There is one way we have arrived at a ending position, hence we return 1 from this case. And for all the paths with the length remaining as this, from this position, view will be basically by adding all the paths from view to adjacency list of u. This is basically all the nodes that are neighbors of u. P is a neighbor of u, which will be given by the adjacency list of u in the question, or we can construct it from the adjacency matrix that is given in the question. So if we take that element, the length decreases by 1, as we saw in the example as well. So this is the straightforward recursive top-down approach. This will take order n times k time complexity, and as we saw, k was up to 10^18. Then it definitely not possible to go forward with this solution. Let's try to figure out something. We tried to figure out the recurrence relation from this function. So as we saw, if you start at any node u, suppose start was u, then the recurrence can be written as this, like this. So you start at u and you have length remaining as k, right? Then you move on to any element v or any node v which is adjacent to u. So for all v which belong to the adjacency node of u, we want, or we get the recurrence as follows. So we have one length path less, and basically this is a summation over all the children, right? This can again be simplified. Suppose, let's see, for a better example, and let's say this. In this case, suppose k was say 2, then dp1 of k would be dp. We can, so if this is u, v can be 2 or 3 because there is a directed path from 1 to 2 and 1 to 3. Hence this would have been 2 with k minus 1 plus dp3 . So this will be dp3 k minus 1 here as well. So this is what you need to look at. And if we generalize this, we arrive at the following recurrence relations. Let me explain them one by one. As we saw, we know the final answer is considering all the starting positions, starting nodes, and counting the number of paths of length k from those starting position, which will be represented by this dp function, and we need to sum over all the paths from this. And dp1 comma k is essentially dp neighbors of 1 with path length k minus 1. So v is a neighbor of 1, and over all of them we need to find out the dp with the second dimension representing path length remaining reduced by 1. And this is essentially the matrix that is given to us. So suppose for the case that we saw in here, for this graph, the adjacency matrix which would have been given in the question would look like this. So 1 is not connected to 1, 1 is connected to 2 and 3, 2 is only connected to 3, and 3 is not connected to anything. This is the adjacency matrix that would have been given us to us in the question. And if you see it clearly, this is the adjacency list of node 1, and only the terms where the matrix has a 1 will be accounted. Suppose as we saw, 1 only has neighbors 2 and 3, but even if you expand this entire summation, only the terms which are the nodes 2 and 3 will be accounted in the summation, because this will be 0 for any node which is not present in the adjacency list. So if node was not present, then this would have been 0 and the entire multiplication would have taken care of that. So similarly, for each of the nodes we will have the same recurrence formula, just that the adjacency list will be different for each starting position. And this is the main idea to represent or introduce this matrix that is given to us in the question in the form of M in the recurrence relation. So as we saw, for the graph with node 1 as the starting position, let's say there are some edges 2, 3, let's say up to anything n, and we have been given a matrix whose, so let's say we only need to know what are the values in the first row which denotes the adjacency list of matrix node 1. It could have been 1 0 0 1, anything here, and this value will basically get multiplied here. Here it will be 0 1 1 and so on, and this is the main recurrence function, the next point of recurrence call. Now let's represent this entire thing in terms of matrices. So we club up all the dp values for all the starting positions u of length k, and this was the matrix adjacency matrix that is given to us in the question. We club up all these values for all the starting nodes, these values. So as you can see, this belongs to 0 and 1 only, and it will be only accountable whenever this term is 1. So m of 1 comma j is 1, then this corresponding entry will be multiplied, right? So if you figure out how matrix multiplication works, on this row all these values will be multiplied to the corresponding values in this manner. So 0 will be multiplied by this, 1 to this, and with the third, and so on. And this is how it follows the same pattern of recurrence that we saw. So this is the same representation of the recurrence relations, and again the answer is basically the sum of all these values, or it is same as multiplying these two terms. And basically we'll arrive at a matrix, and we need to find the sum of all the values present in that. Next up, so as we saw here, This again contains a recursive term, right? So dp of something is again a function of dp of something. This is not completely solved. We don't know the value for this. So let's keep on expanding this further. So if you expand this entire thing, if this matrix is now expanded, earlier we expanded this, we arrive at a similar form. Let's see. If you expand this to k times, this matrix M will be multiplied each of the k times, right? Multiplied k times, and initially we are going to arrive, this has to be 0, my mistake, and we are going to arrive at a base case, which is that if we start at 1 and path length is 0, so all these values will be 1, and this multiplication can be simplified to a exponent. So this are k terms in multiplication, so it is essentially the product of the matrix with itself k times, and these are the base conditions that we saw, and our answer is the summation of all the values will be produced after performing this multiplication. This matrix has a dimension only up to 50 because this is bounded by order n, the number of nodes in the graph, and essentially we can use matrix exponentiation to compute this product. So suppose we are given a matrix which, let's say matrix which has dimensions a cross b, and we need to find the exponent or power of that matrix a cross b to the power k. It can be solved in order, for now let's assume it is a square matrix so that it is helpful in this question. It is solvable in a cube log k time. You can read up about this. It is similar to binary exponentiation. So for any k, let's say the binary representation for it is 1 0 1 0 1 1 1 1 1. We find out the answer for all the powers of 2. So finding out the answer for all the powers of 2 is same as initially starting with only m, which is m raised to 1, then finding out m square by multiplying the previous against itself, then finding out the fourth power by multiplying the previous result with itself, and so on, and you can find out the maximum 2 raised to whatever it is, 2 raised to, let's say 64. My bad, this should be raised to just 64 here, or something like that. 2 raised to 64 for 10 raised to 18. This will be the product of something like this, and we will basically the product of the previous two matrices, and this will give us the matrix powers for all the powers of 2's, and k is basically represented as some powers of 2's, right? The binary representation. So the binary, then we need to find out the summation of all of them, or let's say it was 0 1 0 1, then this was 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3. Now we to find out the value for m raised to k, we find out m raised to 8 is this plus m raised to which is this, which is already computed, and this can be done in order a square log k time. This is the main idea. You can go over other implementations as well. There are multiple blocks available for this online. So let's go over the implementation details now. We are asked to compute the answer modulo 10 to 9 plus 7. This is the constant for that. These two functions are for adding and multiplying the values with modulo. This is the matrix struct. I will provide the link for this in the description as well. So suppose you use a matrix of type int. In that case, this will be initialized with matrix of pointer to pointer. That means it is a to-do grid with the size that is allocated while constructing the grid. So a and b are the dimensions. So these are all the utility functions and the basic operators that are useful for multiplying and performing basic operations on all the matrices. And this is the power function. So this will be solvable. Suppose this has dimensions n cross n, then this function will take order m cube log p time, and p in this our case was k. This we are finding out the kth power of the matrix. So yeah, we take input n and k, then the adjacency list. This is 0 or 1, and we construct the matrix struct from the adjacency list that we pass to the constructor, and then we find out the power of that matrix, kth power of that matrix. And as we saw, this will provide us with this result, right? So after taking the power, we will have this n cross n matrix, and after multiplying all this term individually, we will essentially get the sum of all the elements that are present in this matrix. So we don't need to explicitly multiply this single columnar matrix again. We can simply take the sum of all the elements that are present in this power matrix, which is simply done in this line. We are adding all the entries that are present in this matrix and finally outputting the answer. This was the main idea. We convert the recurrence relation by introducing the adjacency matrix that was provided in the question. There can be different implementations for multiple matrix TP type of problems as well. So this was by introducing this matrix and solving the question accordingly. So first and foremost, it is important to come up with a recurrence relation that you can think of some optimization or any hidden approach that can be underlying in the problem statement. So that was it about this video. If you found this useful, do let me know in the comments, and if you have any doubts or suggestions, do post them in the comments. Thank you.